All right. Hi, everyone. This is our last class meeting before our third exam. Our third exam is going to cover all of Unit 3. So starting with verse with gas laws, moving up until, of course, completing today, solution. I do want to point out all of your homeworks and quizzes are going to be due this upcoming Monday at noon. After you turn in all your homeworks and quizzes, there will be no more homeworks or quizzes before the final, just to give you time to study. But please do what you can now so you're not scrambling to get that done right before the exam. They are going to be very helpful to get ready for the exam, but I'd rather you not be focusing on getting the highest score and actually focusing on doing and understanding what's going on. That's why I push for giving yourself time. So those deadlines are coming up. I did make the third exam. I have made it already. It is the same format as before. It's 25 multiple choice questions covering all of Unit 3. And then there is a short answer portion. It's a little bit longer than previous, but it's the same weight. It's 25%. I also want to point out that I created an equation sheet. If you are online, you can access this equation sheet under resources module. But I will be adding this to your exam. So on your exam, you are going to have an equation sheet and a periodic table element. And I'm giving this to you now. So while you're studying, you can have this with you. So if there is a point where you can't answer a question and it's not on the equation sheet, that's when you know, okay, I need to use it, or I need to learn how to do this. But if you have this equation sheet in front of you and you can answer a question comfortably, that'll be really helpful. Okay, because I'm not going to ask you to memorize any of this. It's just how can you use it. So be able to understand what are these conversions, what are these equations, and when to use it is going to be very, very important. So that's going to be available to you. My goal for today is to finish 3.7 and do a review of the practice exam number 4. Let's finish, or if there any questions, please write them in the chat or ask them. But if there's no questions, let's start 3.7. Last class, we did a lot of solutions where we learned about molarity as a concentration. We talked about concentrated versus dilute, and we did the M1V1 equals M2V2 equation, which is provided on the equation sheet. So we are going to just now connect all the dots from what we did from Unit 1 to now. So can you create a balanced reaction? Can you balance the reaction? And then can you apply solution chemistry to it? So yeah, we saw earlier that the molarity of a solution can be used as a conversion factor. So if I was to say something is 3 molar, you'll see a capital M to represent molar. And you'll notice that as I do these problems, I don't like to leave it like that because the units are more important to me. So 3 molar is the same thing as me saying 3 moles of solute per liters. That's the conversion factor. So 3 moles equals 1 liter. There's no number out front. You can assume it's a 1. For the math, the end of 3, the bottom number has to be 1. So that's how you can use a conversion. So if I was to ask you to solve for moles, you would leave it as is, 3/1. But if I asked you to solve for a volume, you can flip it upside down and solve for a volume, which we did last class. So you can definitely use it as a conversion factor and solve for either moles or liters. So for chemical reactions taking place in solution, stoichiometry calculations can also use molarity of the solution as a conversion factor between liters of solution and moles. So we have to be able to create a balanced reaction and use stoichiometry. So stoichiometry is just the ratio of them to each other. Not everything's always going to be assumed 1. When setting up the calculation, remember that the molarity will turn into a conversion factor. The other information, such as the volume or the grams, is what we might need to adjust before we start. Essentially, turn everything into moles if you have to use stoichiometry. So if I was to give you grams, you have to convert it into moles using the molecular weight with the periodic table. These are better when practiced, so let's practice. How many grams of barium sulfate will be produced when an excess of sodium sulfate solution is added to 25 milliliters of 0.33 molar barium chloride solution? All species in the balanced equation are aqueous except for barium sulfate. So this is a mouthful, but I just want to point out that everything that we have learned so far has prepared us for this. This is the last thing that we are learning in 1320. So it's really combining everything so far. So we need to create a balanced reaction. So let me start by focusing on what our givens are. So it's saying I have an excess of sodium sulfate is added to barium chloride. First, let's create these things. Sodium sulfate. What does that look like? We have NaSO4. What is the charge of Na? +1. What is the charge of sulfate? 2 minus. So does this look correct to you? No. We have to remember to crisscross it. So sodium sulfate will be Na2SO4. And it does say it's aqueous. Then it says I mix it with barium chloride. What is barium's charge? What is chloride's charge? -1. Is this correct? No. Also needs to be crisscrossed. So barium chloride would be BaCl2. All right. It produces barium sulfate. So that would be Ba2 plus and SO4 2 minus. Is this correct? This is correct because you have a 2 plus, 2 minus. It's neutral when you add them together. So I can just take out those charges and leave it as BaSO4, and that's going to be a solid. And then lastly, it doesn't mention what is left over. Does it? Okay. So let's think of this double displacement reaction. So the barium here mixed with the sulfate here. What is left over? What will be the other result? NaCl. The reason why I know it's not Na2Cl2 is one, it's ionic. It's going to kind of reduce down to the lowest number, but Na is plus and Cl is minus. So you don't play around with that. But what I could do to make sure that I have two of them is I put the 2 out front because this does need to be balanced. So I have, let me get a different color. I have 2 sodiums on the left. I have 2 sodiums on the right. I have 1 sulfate on the left. I have 1 sulfate on the right. Don't try to break up the sulfurs enough. Just leave the polyatomic as is. On the left, I have 1 barium. On the right, I have 1 barium. And lastly, on the left, I have 2 chlorines. And on the right, I have 2 chlorines. So yes, I took a few extra steps, but we were able to create a nice balanced reaction, and we can now start the problem. Okay. Okay. So first, we have to always start with our given. And let's reread the problem again, because I feel like this problem can be confusing if you don't know where you're starting and where you're going to. It says I'm starting with 25 milliliters of 0.33 barium chloride. It's asking for how many grams of barium sulfate. So we have to use stoichiometry in this problem because the only way for me to go from one thing to another thing is stoichiometry. I can't just make these assumptions. So let me write this out. Start with your given. 0.33, and instead of me using a capital M, I will always break it down into moles of BaCl2 over liters. That's the same thing as capital M. For me to use stoichiometry, I have to convert everything into moles. That's our goal. When we have to use a balanced reaction, convert everything into moles. So the way this is written right now, it's not moles, it's moles per liter. So I can get rid of the liters in the denominator by multiplying it by liters. Does that make sense? If I multiply it by liters, that's me saying moles times liters divided by liters. Those liters will cancel, and I'm left with moles by itself. So that's our goal, is we need to multiply it by a volume. And the only volume that this question provided us is 25 milliliters. You can't leave it as milliliters, just pointed out, it has to be consistent. So that's 0.025 liters. I divided it by 1,000. So if you need to redo that conversion real quick, let me write this here and then erase it. If I have 25 milliliters and I want liters, it's essentially just dividing it by 1,000. If you want to like just keep going because you're comfortable with those units, that works too. I'm going to break it up a little bit because this question can be confusing. So I don't want to make the assumption that everyone's on the same page with me. So I'm going to convert everything into moles real quick. So 0.33 times 0.025, and that is 0.0800. I now have moles of BaCl2, but I'm trying to get to moles of BaSO4. Why do I know that? Because in order for me to figure out grams of something, I need to have moles of something. Let me clean this up a little bit. I don't have another blank slide, so I'm going to start on the left. And I'm going to continue using dimensional analysis. And this is how you can use stoichiometry. Just a review of what we did in stoichiometry. If there's no number out front, you can assume there's a 1. Even though in your calculator, you probably won't need to put the step into your calculator, it's relevant for this. If you were doing a short answer problem, it's just relevant to be able to see this. I want to cancel out moles of BaCl2. And convert it into moles of barium sulfate. That way, you know, it's a conversion factor. So I have the 1 here, I have the 1 here. I'm just converting one thing into another. So essentially, because everything is 1-to-1, whatever moles of BaCl2, you will have the same moles of barium sulfate. The question, though, is asking for grams. So the last step is to convert from moles to grams using the molecular weight. So let me grab that real quick. I'm too far away from the periodic table of elements. So barium plus 1 sulfur plus 4 oxygen. It's going to be a little heavy. $233. So barium sulfate is 233.386 grams per mole. I got that from the periodic table of elements. That's one way we could do this. I also want to point out the way that I originally taught you how to do this was I kind of combine these two steps. That also works. So if I was to combine these two steps, you would put the number out front. Fix that. So if you prefer the original method I taught you, you would put the number out front, and then you would put what you want, our grams. So 233.386 grams of BaSO4. And it would get you the same answer. But this problem is really good about challenging you. I know that it's asking a lot. Like, let's say if this was on the exam, I probably wouldn't ask you a question with a million things in it. I might have you create the balanced reaction and balance it. And then maybe if I gave you the reaction, I could have you answer this. So it just depends on how much time you have on the exam. I probably wouldn't put it all together, but this is an example of what you would see when you get past 1320. And it's wonderful, because I'm biased, about how everything that we've learned up until now, we are still using it. So that's why I'm really going to push for not cramming, because I know with myself, when I was in your shoes, I feel like when I graduated my bachelor's degree and I went for a job, I lost all of it because I crammed for everything. I wanted to get the grade, but I didn't even care about the material. So it's more important for you to get comfortable with the material versus doing what's necessary to pass the class, if that makes sense. Because when you hit Gen Chem or Engineering Chem, you're going to see this over and over and over again. So this is an example of what you would see when you hit Gen Chem, maybe Gen Chem 2, maybe towards the end of Gen Chem 1, but you can still see that we're adding and building and building and building. So if you're comfortable, at least with the first part, as you continue practicing and practicing and practicing, you're just going to get better and better and better. And that's why I love chemistry. It's all about, I consider it bullshitting. It's about knowing the basics, and you can throw me a problem. I might be really rusty, but I can at least get most of it there. Versus biology or other sciences or like history. You either know it or you don't. Do you know the year that this war was at? I don't know. But in chemistry, you can use your basics to answer things. Okay. Number 2. I'm going to have y'all start this problem. I want you to first create a balanced reaction. Read the question really, really well. And if you want to start the math, we can start the math. But if you don't, you can wait for me. But I think first, let's start by creating a balanced reaction. I'll give you a minute or two. So this says baking soda, which is sodium hydrogen carbonate. Does anyone know what carbonate is? Close. Yes, CO3. I feel like our initial reaction, like it's just the opposite. It's like you're so close. One less or one more. And that's CO3 2 minus. So sodium hydrogen would look like this, NaHCO3. So this is why I'll show you, this is more an advanced one, but sodium is a +1 charge. Hydrogen is a +1 charge. CO3 is a 2 minus charge. So there is no crisscrossing required here because I have 2 +1s and a -2. So I will write this all out. So Na HCO3. So it says NaHCO3 reacts with hydrochloric acid, HCl, to produce sodium chloride, water, and carbon dioxide. So I actually made the mistake and put a 3 here. Carbon dioxide is a 2, not a 3. Is this balanced? Wait, yeah, no, 1. Oh. Is this balanced? Yes. You can see how easy it is to get tricked because you saw me get tricked. That's okay. Just double check and make sure you have the same number on both sides. And in this case, everything has a 1-to-1 ratio. I love it when everything is perfectly 1-to-1. It makes the math so much easier because if you forget to use stoichiometry, you're still right. Now let's set this up. Let's read the question again. How many liters of carbon dioxide? This requires us to remember the mole triangle, where 1 mole, do y'all remember the number? Yes, 22.4 liters of gas. All right, how many liters of carbon dioxide? So we're going to try to produce carbon dioxide. Can be produced by excess by baking soda and 100 milliliters of 0.1 molar HCl. So we are starting with HCl and we need to convert it to CO2. The way that we do that, to use stoichiometry, you have to get everything into moles, and then you can do a mole to mole conversion using stoichiometry, and then convert everything into CO2. So first, we have a concentration of HCl and we have a volume of HCl. What do I have to do to get moles? Yes. So once again, I don't like leaving the capital M because I just like units. So I'm going to take out that capital M and replace it with its definition, moles of solute per liters. To me, that makes it more doable to get rid of it and focus on moles. So if I have 100 milliliters, how many liters is that? Yes, 100 divided by 1,000 is 0.1 liters. Reminder, don't leave it in milliliters because this will not cancel out if they have different units. That leaves me in moles of HCl. If I want to convert it into moles of CO2, I would do what we did before. So the stoichiometry comes out front, and in parentheses is kind of what you want divided by what you're given. So we've already done this a bunch. And then last class, we did this a bunch. So we're just combining them. Check my math just in case I didn't calculate correctly. But yeah, that's it. We finished all of the lecture components for 1320. You're done. The last thing we have to do is just put it all together and get ready for exam 3. So, let's look at exam 3 or the practice exam. Just remember, I will be giving you this equation sheet. I highly recommend while you're studying, you have this equation sheet in front of you. Don't add any notes to it because you won't have those notes on your exam. So try to use this as a reference while you study. Yeah, so here's what I'm giving you on the exam. So I'll give you these conversions. I will give you these equations. If you are in person, I gave you exam 4. If you are online, you can download exam 4 from our exam modules. It's the exam 4 from fall of 2024. But I would like for us to go over it together. But I do want to point out on this exam 4, it is missing a couple of units. It looks like it's missing unit 3.1. It's missing unit 3.7. And I think it's missing maybe the light portion of 3.2. It is missing that. So just make sure that you're not just using this as a way to study, because I will be asking, and I already made the exam, so I know I will be asking some questions on the diverse using gas laws. I will be asking a light question or two, and you'll definitely have some solution questions in there. Maybe not as difficult as those last 2 slides, but maybe broken down. Okay. Every question on this exam could be, a good reference. So I do want to take time to go over things. Number 1, which of the following statements about subatomic particles is not correct? Subatomic particles are neutrons, protons, and electrons. Remember that neutrons and protons are at the nucleus, the center of the atom, and electrons float around it. So let's just discuss real quick before we answer this. The weight of the atom comes from the neutrons and protons. It does not come from the electrons because they are so tiny and light. They don't actually affect the overall weight. So just double check, because if it was to say the weight is the combination of electrons and protons, that would be a trick. It's combination of protons and neutrons. So which of the following statements about subatomic particles is not correct? A, neutrons are the only particle found in nucleus. That was pretty quick. So I will point out, if you have plenty of time, definitely read through all the answer options and isolate what makes no sense. But if you're running out of time and answer option A is the one that's not correct, just move on. But protons and neutrons have approximately the same mass. Yes, because if you add them up, they should be around the same mass. We just say 1 atomic unit per proton or neutron. Protons and electrons have opposite charges. Absolutely. Protons have a positive charge. Electrons have a negative charge. That's true. Electrons are found in orbitals outside of the nucleus. Absolutely. They are not in the nucleus. So I think that, let's say answer option B was a little confusing to you. I get that. It can be confusing if you're not 100% sure about the weight, but I know answer option A is more correct, meaning that it's definitely not correct according to the question. So I would recommend your instinct telling you, don't second guess yourself. If you're confused about it, don't try to make it work. Just focus on what you do know. So I'm moving on to 2. Which combination of protons, neutrons, and electrons is correct for the isotope? I love this question. So here is the element. The bottom number. Can anyone tell me what that number represents? Protons, neutrons, or electrons? Huh? Protons. So this number will always be the same for that specific element. So if I was to change elements, maybe didn't carbon, nitrogen, it doesn't matter. But this number here is the atomic number of that element. So if I go to the periodic table of elements and I look up number 29, I will see copper. So protons and atomic number are the same. This number here, this is not protons, neutrons, or electrons. This number is the combination of protons and neutrons. This is the atomic mass. So to get this number, I have to add protons and neutrons. So like if I was to say like 63 is the neutrons, that would be absolutely untrue. If I said 63 was the protons, it would be absolutely untrue, which means I can go in and take out answer option B and answer option A because I know the bottom number is protons. So I'm looking at the front here, like it can only be C or D. So the next step is to figure out the next one. Now, is this copper the way it's written charged? Okay. If there was a charge on here, it would be written in this top right corner right here. But since there's no number, I can assume it's neutral. There's no charge. If it's neutral, the amount of electrons will equal the amount of protons. Does that make sense? So then I can go here and say if my electrons and protons are the same, then it's neutrally charged. So the only answer option is D. But lastly, I would like to confirm, for me to figure out my number of neutrons, so protons plus for me to figure this out, if I took 63 subtracted 29, that would give me 34. That's how I know for a fact D is correct. But even if you don't know how to do that, we were able to deduce what's correct because at least I know the electron portion of it. So maybe you're comfortable with knowing atomic mass and protons and you don't quite know electrons, you could still answer it. Just note that this number has nothing to do with electrons. Nothing. Don't let it confuse you. All right. Number 3, I want y'all to answer it. Which of the following pairs are isotopes of the same element? So look at them, and I'm not trying to confuse you here. So when you get to this problem, I want you to be able to immediately know what's going on because I don't want you wasting time trying to do any math here. So isotopes are going to be the same element. How do I know that? Or how do I know which one's the same element? Look at the bottom number. If the bottom number is different, they're different elements. Remember that I said the bottom number is the atomic number on the periodic table of elements. So 6 and 7 right here, that's not an isotope. That is literally carbon and nitrogen. Carbon and nitrogen. 9 and 8, that is oxygen and fluorine. 6 and 6, oxygen and oxygen. So I'm putting an X in there to just represent a generic element, but the only, out of all these options, the only one that's the same element will have the same number in the bottom. So this question is not trying to trick you, but you can answer it very, very quickly if you understand that. Look at the bottom numbers and that tells you if it's an isotope. Isotopes are the same element. You're not comparing nitrogen 14 and oxygen 16. That's just not that's not an isotope. An isotope is hydrogen 1 and hydrogen 3. They're the same element. So that bottom number will be 1 for both. So. Okay, here is a great question because it goes off of electrons. Remember, electrons are the same as the protons if it's neutrally charged. And electrons have a negative charge. Okay. The charge is given to us that titanium is a 4 plus. If titanium was neutral, had a 0 in that top right or no number in the top right, then 22 would be the amount of electrons. Sorry, it can't be 22 because it's not neutral. If titanium had 4 extra electrons, it would be a 4 minus. The more electrons, the more negative because they're negatively charged. So if it was titanium 4 minus, you would have 4 more electrons. So 22 is your neutral. So 26 cannot be right because 26 would be if it was a 4 minus. So for it to be a 4 plus, I have to remove 4 electrons. So subtract 4 electrons to make it more positive. So that means D has to be the right answer. 44 is the weight. It's about, I think that number is coming from the weight. So don't get tricked. Use the bottom number. Use the proton number, not the atomic weight number. So if I was to ask you a short answer question, and I'm gonna like save a little time right now. Let's do nickel 2 plus. How many electrons are in nickel 2 plus? So nickel is 28. If it was neutral, it would have 28 electrons. So if it's a 2 plus, it would have to be 26, correct? How many electrons if I have carbon that's neutral? So if carbon's neutral, how many electrons? 6, yeah. What if it's carbon 4 plus? So it would be 2, right? Yeah. What if I have phosphorus 3 minus? Yes. So what would that number be? Yes. All right. So if it's a minus, you add those electrons on. If it's a plus, you remove them. I like this question. Be prepared to see it because I'm really testing how comfortable are you knowing about those charges and where the electrons are coming from. Okay. Now, number 5 can be a little unique. So when we talked about the way that elements compare to each other, I don't know how this works in the world because it just seems that this periodic table of elements is just so convenient. And I'll explain that in a moment. So what we're saying that all of column 1 are very similar to each other because I said naturally they want to have that +1 charge, right? Column 2, +2 charge. So when I'm comparing elements to each other, the ones that are the most similar are going to be on the same column. I have no clue how that worked out, how conveniently they're next in row, the protons are working out, their identity are working out. It's just beautiful. I don't know how that existed in life, but I'm happy about it. So if I was to ask you this question, I'm just asking you which 2 are on the same column. What answer is it? Yeah. Lithium and beryllium are right next to each other, so that's column 1 and 2. It wouldn't work. O and F, oxygen's column 16, F is column 17, would not work. Sodium and nitrogen are way off. We have a metal and a non-metal, that could never be it. Calcium, magnesium are both column 2, so it has to be D. So just a reminder, I'm not trying to like really trick you with these questions. I'm not. Sometimes the simplest answer is the best. So don't focus on the row, focus on the column. Which of the following statements describes Rutherford's gold foil experiment? Do y'all remember when I talked about that? Okay, this is a great question. I know that it's hard for me to ask if you weren't here in class that day or if you didn't see my lecture, like it's a hard question, but let's see if you can remember it. The way that I would answer this question is kind of like, okay, what's true and what's not? So number 1, scientists scattered small pieces of gold foil in a magnetic field to observe the spin of the electron. Does that sound right? No. So number 1 cannot be right. So I'm going to go through and remove anything with the number 1. So we've already instantly given ourselves a 50-50 shot. Number 2, a beam of alpha particles was directed at gold foil. Is that correct? Yes. So number 2 has to be in the answer. So B and D both have a 2. Okay, let's move on. The scientists in Rutherford's lab did not correctly predict the results of the experiment before actually running the experiment. You think so? Okay, so I'm going to question mark because it might or might not be true. It seems like it could be, but I'm not 100%. Maybe the last one will help us, know for a fact. The results of the experiment supported the plum pudding model of the atom. So the plum pudding was when they assumed that in a atom, let me do plum, maybe. So plum pudding. They just assumed that the electrons and protons are just floating around there together. They didn't know where things were. So in this experiment, we shot alpha particles at this thing. In reality, they didn't really, they proved their hypothesis wrong. They thought it would be like this, and so they thought that every alpha particle would go straight through. But if you remember, some of those alpha particles bounced back at them. So 3 was correct, meaning that the 3 was correct, that the scientists in Rutherford's lab did not correctly predict these results because those alpha particles came back at them. Number 4, the results of the experiment supported plum pudding? No, because if it did, they wouldn't be hitting that nucleus. So what happened was those particles hit the nucleus and it shot back at them, but the nucleus was so small that it happened maybe 1 in every 1,000, 2,000 alpha particles. So the answer is going to be 2 and 3, not 2 and 4. So I would think 3 would be more right, but this is more of a memorization question. But at least we were able to give ourselves a 50-50 shot here. And at least you can kind of make a deduction here. So it's not, if you were to accidentally guess right or wrong, it's not the end of the world. So this one, it's going to be B because of what happened in the experiment. Did Dr. Patterson talk to you about radius when she was teaching? No? Possibly. I don't, if she didn't talk about this, we can kind of make a deduction based on that hint she put. Which of the following atoms have the largest radius? And it says, consider the last subshell notation for each element and compare the orbitals involved. So what we're saying here is that as you add more subshells, the bigger and bigger the atom. So hydrogen only has a 1s. So let me say like hydrogen, 1s1 would be the electron configuration. But if I was comparing it to like potassium, they're both column 1, but which one's bigger? Potassium is. So with this question, it's asking you essentially to see like which one's furthest down the periodic table of elements. So like find barium, find calcium, find magnesium and strontium, they're all in the same row. So just like comparing hydrogen versus potassium, as the orbitals get bigger and bigger and bigger, so 1s, 2s2, 3s2, 4s2, 5s2, the radius gets larger as we go further and further down the rows. So magnesium, calcium, strontium, barium, which one's the largest? Barium's the furthest down. So I love this question because I know that we didn't hit on radius. You're going to hit on that when you hit Gen Chem, but we were still able to make logic and make a rational deduction by just saying, okay, the bigger the subshell, the bigger the size of the atom. That's why hydrogen is going to be the smallest because it's, it only has 1 electron. There's no reason for that electron to be way out here because as you add electrons to it, you'll start to have bigger and bigger subshells and more space. But yeah, so this question, it would be all in the same column. Just note the further down the column, bigger it is. Number 8, which family in the periodic table contains elements which all have the final subshell notation number that N represents number S2? So that's what I kind of just had up here. 1s2, 2s2, 3s2, 4s2, 5s2. So that N just represents a random number. So which family or column does that represent? Don't remember? If you don't remember on top of your head, look at your answer options. Like, do you know where the halogens are? Is the second column the halogens? No. Is the second column the noble gases? No. So for me, I've eliminated 50-50 shot, and I just got to figure out, is it alkaline earth or alkali? It would be alkaline earth. So column 2, alkaline earth. Column 1, alkali. Now, I could also ask the same exact question, NS1. That would be alkali metals. So we did that one. If I wanted to write this question for halogens, what would I write? Yes, NP5. Because it's the fifth in the P block. All right, what about noble gases? P6. So you can see how like this question can be rewritten a million different times. All I would have to do is change things around. I can say chalcogens, NP4. I can say transition metals, anything in the D block. So I can ask this question and change it around, but I give you the exact same type of question. Just know the N represents any row, but we're focusing on the other two letters. All right. Maybe we have time for another question before we have our break. How many electrons could go into the 5s subshell? So each element is one electron. So find 5s. How many elements are in the 5s? 2. So the only electrons that can be in 5s are 2. 5s2 is the maximum. So this one would have to be 2. If it was to say, let's say 4d, how many electrons? 10.
So the D would be the block, right?
The transition metal block, yeah. What if I said P block? So let's say I said 2p. How many electrons? Does anyone know what 14 would belong to? F, yes. So I can ask you this question in a bunch of different ways, but you can still answer it. So if it's S block, it's 2. If it's D block, it's 10. If it's F block, it's 14. If it's P block, it's 6. All I have to do is change the number in front of it, but that's how you can answer this question. So it's 12:50. Let's have a 5-minute break and we'll come back and continue on with this practice exam. All right, let's continue. Number 10, this one just requires you to remember the shape of everything. I do want to point out the shape of the S block is just a circle. So if it was like to ask you the same question and I had just a circle as the shape, then what answer option would that have to be? It would have to be A, the S block. This belongs to the P block, D block, and F block. So you need to be able to identify the picture. Now, the D block look like a pair of dumbbells, and the F block kind of looked like this. I can't draw. We didn't really go over this in lecture for the F block. So we have the D block here and the F block here. This is for the P block. So we have S, P, D, and F. So this one would just require understanding what the picture looks like. So what answer do you think it has to be? it has to be B, because this picture belongs to the P block. That means B is the right answer. But just remember, if you don't have this memorized, at least you can kind of eliminate what makes no sense. So I could definitely eliminate A and D. I have no clue what that block, we didn't discuss that really. So I could eliminate that and give yourself a 50-50 shot between B and C. Because P and D block look very similar. It's just D block is just a double barbell. Okay. Now, 11 is a great question because it just requires you to be able to understand how to do valence electrons. So it says a hypothetical element has this following electron configuration. So it's very far down on the periodic table of elements. And it asks for how many valence electrons. It's tempting to just count all of these electrons, but I want to point out that valence electrons are the last number of the column. So the noble gases are on column 18, so their valence electrons will be 8. Let's look at nickel. Nickel is on column 10, so the valence electrons would, in that case, it would be 10. If it's inside this D block, you would have to incorporate those. But in this case, if you start incorporating the P block, you have to just figure out where it is on the periodic table and then count where the columns are. So if it's a P3, that means it's under nitrogen. That means it's column 15. Or wait. 1, 2, yeah. Yeah, okay. 15. I'm like, why don't I see 15? But it's the last number in the column. So that's why this one has to be B. So if I do ask this types of question, if it's in a P block, you ignore the D and the F block. If it's in the D block, you would not ignore it. You would incorporate S and D block. But if you're in the P block, you only have S and P. I know that's a confusing question.
So if it was like a D3, if that's what it ends in, it would also be 5?
Yes, if it was D3, because you have the 2 from the S block, and then you're on column 5, so it would be 5 valence electrons. That's how I would kind of answer it, is figure out where it's at on the periodic table of elements and look at the last column number. Because I feel like if you were doing that based on this, I think if you started incorporating I think it'd be too confusing. All right, number 12. When writing the electron configuration for nickel, what is the last subshell notation written? So if you are comfortable with the noble gas configuration, I highly recommend doing the noble gas configuration for these types of problems because it's a waste of time to do everything. It's asking you the last. So let's write the noble gas configuration for this. What is the noble gas before nickel? Argon. Because now we can start on the next row that nickel's on. So what will be, what would I write first? 4s2 and then? Yeah, I wrote the wrong number. 3d8. So what has the answer? Like, what is the answer? It's D. There's no such thing as a P that's beyond 6, so it can't be that. And then we know it's on the 3D row, so it has to be D. Not so bad. So I can ask that question and just put any element in there and just see what y'all can get.
When we're looking at the D block, it's the n-1, whatever. It's like it's on the 4th row.
Oh yeah,
but
so
the-
yeah, so it would just start at 3. So this is 3D. Even though it's on the 4th row, it goes 4s2, 3d10, 4p6, so it's a 3d, 4d, 5d, 6. what does the symbol helium in brackets mean in an electron configuration? So if I just have helium and I don't go any further, what would that look like? Okay. If it's helium that's neutral, it would be a 2 in the bottom, which means it has 2 neutrons, but I don't really know about the weight here. I mean, I could incorporate the weight up there and say He4. So like, but it's not asking about really a lot of electrons and neutrons. It's asking about the electron configuration. So yes, there are 2 electrons, but which one is the most right when it comes to electron configuration? Just the 1s2. So I think like with this one, like all of the answer options look right to me, all of them. But this is one of those questions that asks you for like, what is the most right when it comes to the electron configuration? If I was to like give you this with the way that it's written right here, then you can answer it the other ways. But I think with this one, like, I'm not trying to challenge you, just keep it sweet and simple. If it's, I'm asking about electron configuration, which one's most like electron configuration? All right, I'll give you all a minute to answer number 14.
Ground state is asking like when it's neutral.
Yeah, ground state would be it's not excited, it's neutral.
Okay.
Yeah. That's a great question. With this one, I kind of would just go on the periodic table of elements and go find 3p2. Like I wouldn't even like, if you feel more comfortable starting from the rows and like reading it like a book going left to right. So 1s2 is hydrogen helium, 2s2 lithium beryllium, 2p6 all the way to neon, 3s2 sodium magnesium, and then 3p2, that means silicon. So like if you prefer to read it like that, that works. Read it like a book. But for me, as I'm more comfortable, I would just focus on the last one. If it says 3p2, I would go find the 3p2 row and count to 2 electrons. That's how I would do that one. So this one would have to be silicon. And it's okay if it takes you longer than what I'm doing. I've just seen this more. It doesn't mean that. If you're able to answer this question like on the exam, you're good. You don't have to answer as fast as me. Let 10 go. When writing the shortcut version of the electron configuration for strontium, strontium is number 38. Oh, it says that. Which symbol serves as the core? So this is like just testing your comfortability with noble gas. So find strontium and then find the noble gas in the previous row. Yes, it would be krypton.
Just the one that's before it, right?
Exactly. It's so much simpler than it seems. So you just find the noble gas on the previous row, and that is the answer. Okay, a hypothetical element has the following electron configuration. How many valence electrons? Yes. So S block is super easy. Whatever number that it gives you, that is its valence electrons. It's when you move into the pass blocks, you start to have to like think about it. But essentially, like it would be on column 2. I can look at here and just instantly know if the S block is filled, it's column 2. And so the amount of valence electrons in column 2 is always 2.
Is that simply given? Whenever you say if it's on column 2, it's always gonna be 2.
Yes. So column 3, always 3. Column 4, always 4. Column 13, always 3. column 15, always 5. So it's the last, yeah, so that's why I say like identify where it's at on the periodic table of elements, maybe what row it's, the column it's on, and that's how you can count valence versus just looking at the electron configuration. Once you get more comfortable, you can look at the electron configuration. But I do recommend like having the periodic table of elements with you and focusing on that. So if I was to say how many valence electrons, if it is I don't know, 7D10 F. I don't know, number F14 7P5. How many valence electrons in that one? So what column is that on? Focus on the very last thing I wrote, 7P5. What column?
It'd be on, oh, that's not called five, right?
Is it? Find, where's 2P5? Where's 3P5? Where's 4P5? Where is P5?
Oh,
17th column, yes. So it would be column 17. So remember, you don't just count it from the beginning. The P5 represents P1 would be boron's column. P2 would be carbon's column. P3 would be nitrogen's column. P4, oxygen's column. P5, fluorine's column. So if it's in column 17, how many valence electrons? 7. Yes, I can ask this a billion different ways. Let's do OG8S2 7D7. How many valence electrons? Find where the column is. If you feel more comfortable ignoring the 7 and doing a 2, or sorry, 3, where's 3D7? What element is 3D7?
is this not called?
It's cobalt. Do you see that? So scantium is column, or is 3D1, titanium 3D2, vanadium is 3D3, chromium 3D4, magnesium 3D5, iron 3D6, cobalt 3D7. So essentially this would be on cobalt's column. So what column is cobalt on? Like if you count it from the very beginning, how many columns is cobalt? Yes, Mercedes. That's how many valence electrons. Yeah, because it's in column 9, it would be 9 valence electrons. So like I can ask this question a million different ways to really challenge you, but you just got to focus on what column it's on to answer this question. Don't let this fluff challenge you or confuse you. Find where it would be on the periodic table of elements and focus on the column. So this is just a good way of me giving you an unknown element, like an unknown, but still have you make those deductions. Okay. Here's an easier version of the same exact question. How many valence electrons are in chlorine? Essentially, what column is chlorine in? Exactly, it's in column 17. It would have 7 valence electrons. Perfect. When writing an electron configuration after the 5s subshell is filled, what subshell is used next? So find row 5, that would be rubidium. So once I fill rubidium and strontium, what is the next element? I know it's a weird pronunciation. Yttrium? Yttrium, do y'all see why? What is Y? Would it be the 4D, the 5F, the 5P, or the 5D? Yes. So 5P would be the next, or 5D would be the next row. But after 5S, remember it drops down to 4D, just like after 4S, it drops to 3D. 4D. When writing the electron configuration for sulfur, what is the last subshell notation that's written? What do y'all think? Is it A or B? Yes, if it was B, then it would not be sulfur, it would be argon. But sulfur would be 3P4. Okay. I really like 20 because it's a challenging question, even though we haven't really hit on it. A scientist proposes a new set of atomic orbitals. So it's a brand new set of atomic orbitals, as shown in the orbital energy diagram, level below, or below, blah, blah, blah. In this new theory, these orbitals replace the s, p, and d and f orbitals that we have learned about. Follow the same rules. So the same rules would be go from bottom to top. And then it says do it for neon. So first, how many electrons does neon have? What is its atomic number? 10. So it's not saying neon has a charge. So if I can assume neon is, neutral, it'll have 10 electrons total. So that means that I need to start bottom up and add it until I hit 10 electrons. Just note, if I have multiple side by side, I have to fill it out first before I go back and add the second one. There's 2 per orbital. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because if you didn't know to do that, to fill it out that way before you add the others, that will give you a different number up here. You'd have them both here, but that's not true. You have to fill it out first. So this would be the new electron orbital for neon. And the question says, if this new set of orbitals is correct, how many unpaired electrons does neon have? Is this a paired or unpaired electron set? This is paired. So we can ignore these. These are all paired. So there's how many unpaired? 2. So this question is doable if you just pretend it's the same way we've been doing it. Start from the bottom and work your way up. Not so bad. Okay, so this one does actually ask you about light. The blue-green light line of the argon ion laser has a wavelength of 488 nanometers. Express this wavelength in meters. Does anyone remember the conversion factor between meters and nano? Yes, it's a billion. So if I was to create a conversion factor, 1 meter equals 10 to the 9th nanometer. If you prefer to have the negative in there, that would go on the meter side. You kind of have to pick which one you prefer. I like this one. So 488 nanometers times 1 meter over 1 times 10 to the 9th. Yeah. Go ahead and type that in your calculator. What'd you get? Hopefully you got D. Okay, good. It should be very small. Because you're moving this decimal place over to the left 7 or 9 times. Oh, number 22 is fun too. Which of the following measurements is the biggest? So a centigram, a nanogram, a milligram, or a microgram? Yeah, it's centi. So there are 100 centigrams in 1 gram. There are 1 times 10 to the 9th nanograms in 1 gram, 1,000 milligrams in 1 gram, and 1 times 10 to the 6th micrograms in 1 gram. These are all very small numbers. So the biggest out of all of these would be centi. This one's a good challenge. You can always plug this into your calculator and get the right answer, because what I would do here is they don't give you a number here, but you can just say like 10 to the 6th divided by 10 to the second, and you'll get a number. You can put any number in here and you'll get a number. But the way that I think it wants to challenge you is remember that if I was to like multiply 10 to the 6th times 10, a number to the 6th times a number to the second would be x to the 6th plus second, right? Right? Or double, yeah, 8. If I divide it, it's the exact opposite. So for this one, it would be x to the 6th minus the second, right? So yeah, if you can't hypothetically do this one, plug in numbers. Plug in 10. 10 would be a good number to plug in and see what it gets you. Let me do that now. I always will do that. If I want to test my theory and say, okay, is my theory right? Put in some numbers. So if I just do 10 to the 6th divided by 10 to the second, yeah, I get 10,000, which is 10 to the 4th. So I can do it with numbers too. Like let's do 2 to the 6th divided by 2 squared. I get 16, which is 2 to the 4th. Yeah. So just remember, if I multiply something to the exponent to something to the exponent, you add the exponents. If I divide, you subtract. Almost done. There's 32 questions. We're going through it. Diatoms are microscopic forms of algae. One particular diatom is 150 micrometers in length. How long is this in millimeters? So remember we talked about doing conversions 2 different ways. You can convert it to the SI unit and then convert it to the new unit, or you can do it all at once. So if I have a micrometer, or yeah, so how many micrometers are in 1 meter? A million, yes. So 1 times 10 to the 6th micrometers are in 1 meter. And if I have 1,000 millimeters in 1 meter, we can figure out the distance here. So okay. So this is micrometers, this is millimeters, and this is meter. What is the difference between these 2 numbers?
What do you mean?
So if I was to go from 1 to this is a million, right? What's the difference between these 2? 1,000. So this is, if you feel very comfortable with math, you can kind of skip this double step conversion. But if you are very comfortable with math, you can kind of, sorry, I think I'm saying things weird. If you want to be 100% sure and you're maybe not as comfortable, you can go, I would convert from micrometers to meters and then from meters to millimeters. If you're very comfortable with math, you can kind of get comfortable knowing that there are 1,000 micrometers in 1 millimeter, just by knowing the difference here is 1,000. They'll both give you the right answer, and I'll show you both. That's one way you can do it. Oh, I messed it up, sorry. This one needs another M. Both will give you the right answer. It just depends on how comfortable you are with the setup. So it's essentially 150 divided by 1,000, so that's 0.15, I assume. Perfect. B. This is a fun question. We're still on conversions. A problem asks you to convert 2.7 kilograms to milligrams. Which of the words below best describes how the numerical answer to this conversion compares to the number 2.7? My honest advice is just to do the math, because if you try to conceptualize it and you're not very comfortable with these numbers, I would probably do the math, because you might kind of be on the right track, but like for some reason your brain flips it. So first, let's convert kilograms to milligrams. So just like up here, we can break it down and do 2 steps like right here, or we can just do it all in one. It just depends. The difference between this is a million, because the difference between kilograms to grams is 1,000, grams to milligrams is 1,000. So this is a million. So would you rather me do it in 2 steps or one? You want to do in two? Okay, well, let's do in 2 steps. So if I do this math correctly, 2.7 times 1,000 times 1,000. Would that be a bigger, the same, or smaller number when I do the math? Like 2.7 million. So is that number bigger than 2.7? Then the answer will be bigger. So this might seem like a very complicated question, but it's just asking you to compare to 2.7. Is the new number bigger or smaller? It's not going to be the same. So 2.7 million is a lot bigger. So that means that if I was to convert a kilo into milli, you'll have a much bigger number. If I go backwards, milli to kilo, it'll be much smaller. But if you can't conceptualize this, no worry. Let the numbers answer this for you. And then I'm going to give you a minute to answer number 26 by yourself. It's another conversion question. It's just written to kind of like challenge your ability to do conversions. So it just gives you a new unique conversion factor. It's just dimensional analysis, but I love it because it's not really something rational. It's talking about aliens. So if I have 1.6 arms and the conversion is 11 heads to 3 arms, you would just set it up like this: 1.6 times 11 over 3, or 1.6 times 11, enter, divide by 3. So I think that would give me C. Did y'all get C? I'm guessing. I should probably do the math too. Right? Okay. Go me. Is that in my head? Yeah. Ooh, number 27. Which of the following equivalents is wrong? Yes. So there are 1,000 millimeters in 1 meter, but this can also be written as 1 times 10 to the minus 3 meters. There are 1,000 meters and 1 kilometer. That's correct. There are 1 billion nanometers and 1 meters, but the opposite of that is written like this. And so that means that, there are not a million meters in 1 micrometer. That's just that it's the opposite. So there are a million micrometers in 1 meter. So this is a good challenging question. So the answer has to be D. In some problems, you must determine what property a measurement describes from its units. Which answer below identifies a property that does not match the unit of measurements? Oh, this is a good question. So it's combining, I do want to point out, it's combining prefixes like nano, micro, C is for centi, M is for milli. So if it's a prefix out in front of a unit, don't get tripped up if it's something we haven't seen yet. It's just a prefix. So focus on the unit itself. For instance, centiliters, is that a volume? It is. If you prefer to leave it as liters, liters is a volume, millimeters is a volume, milliliters is a volume, so centiliters has to be a volume. Microseconds, is that a time? Yeah, anything with a second is a time. Length, nanometers. It's a meter, so length is meter. Mass, 250 millimoles. A mole is not a mass. A mole is an amount. So remember that. You have grams for mass, pounds for mass. There's other ounces could be mass. Yeah, fluid like ounces is definitely a mass, but moles is not a mass. Mole is an amount. So the good news is if you can't initially understand that, we were able to eliminate the other answer options by being like, definitely those have to be true. So that makes that A can't be true. All right. I want y'all to go ahead and balance this one. Okay. So when I balance this one, because I have a P4 over here and a P2 over here, I'm gonna double it so I can have 4 on both sides, which means I now have 6 oxygen, and that means I have to have 3 O2. So that's the balanced reaction, and it asks you to add up all the coefficients. So 1 plus 3 is 4 plus 2, and the answer has to be D. All right. Y'all go ahead and answer this one because this is how like I might ask this question on our exam. So this is very, very similar to what we did on the last exam. So it's straight review. Y'all answer like 30 and 31. Yeah, go ahead. Or actually, you can answer all of these. So I'll give you a few minutes to answer all of these. So let's review, if I'm going from moles of one thing to moles of the other, I need to have the number out front. So 6.94 moles of NH3. I want my moles of NH3 on the bottom, so that stoichiometry comes out front. And it's asking for water. So 6 times 6 divided by 4, so that's 7. I don't know that number on top of my head. Okay, it's gonna be C. Check my math. And this one says going from grams to grams. So you still need to have this math for this, but we need to also have the molecular masses. So that's probably the easiest things to solve for. O2 is 16 times 2. NH3, you have 14 plus 3 hydrogen. So how many grams of oxygen are needed? So if I have 25 grams of NH3, and I want to get grams of oxygen, I need to have my stoichiometry out front, and then I do the molecular weight. Yeah. That's how we kind of learned doing stoichiometry in us, when we did the stoic section. $58.7. Oh, I did the wrong numbers. Did y'all catch that? How many O2? There's 5. So I just want to point out that this math is the same thing as this math. It's just I'm kind of breaking up into its different steps. So this math is, if you feel more comfortable knowing, okay, well, if I'm going from one thing to another using the mole triangle, where you have, your moles in the middle, you have your, I think up top was like molecular weight, you have your STP 22.4 liters of gas, and you have your amount, so your 6.02 times 10 to the 23rd molecules or represented particles. That's one way of doing it. So you just take the number out front with the balanced reaction and put it out front of that. This is the same way of doing the math. So, this is a good way of also checking your units. My grams of NH3 cancel, moles of NH3 cancel, moles of O2 cancel, and I'm left with grams of O2. So if you feel more comfortable doing it this way, that's how you can save steps and get the answer in the end. We only have 3 more minutes left of class, but I do want to point out that this practice exam is missing using verse for gas laws. So that's why I included the ideal gas law. Remember, when we use this equation, it's when you have one of everything, so maybe one pressure, one volume, one temperature, but you use this equation when you have two pressures, 2 volumes. And if they don't include something, let's say I only give you pressure and volume, you would take out the temperature and you have P1 V1 equals P2 V2. If I just give you pressures and temperatures, you can take out the V's and get P1 over T1 equals P2 over T2. So that's important to be able to use this. And R, if you need to use ideal gas law constant, that's given to you up here. I also noticed there's no light equations in here. So there were some conversions going from meters to nanometers, which you still need to be able to use. But if I ask you to solve for frequency, that's this right here, frequency. If I ask you to solve for wavelength, that's here. If you need to use C, C is given to you up here. If you need to solve for energy, capital E, both of these equations will get you the right answer. And Planck's constant is given to you up here. And then there were no dilution equations. You might have to do a dilution equation. That's here. And then if I asked you to calculate the average atomic mass, you use this equation. Okay. So have this with you as you're studying. because you can kind of focus on like, what am I not gonna have you memorize is, and then it's gonna help you. Just don't put anything on it, so you're only studying what I give you. Any questions? So lambda equals, yeah. It- I can give it to you in anything, but if you're going to use this equation, you have to convert it to meters because the speed of light is given to you in meters. You have to convert it to meters. Okay. All right, so I will see y'all next Monday. Just note, I will be in my office in the morning. You're welcome to pop in and ask questions. But it will cover all of Unit 3. Even if this practice exam doesn't have it, you might be tested on it for mine. Alarms off. Okay. Good luck studying.